now on I'm going to be explaining to all of you the principle of resonance.
My name is Luis Chavira and I will be presenting to you Bernoulli's principle.
I would like you to turn to the page that has a 1 at the top. So if you're on side 2, please turn to side 1. I'll be explaining, something that most kids face at our age level. We'll be doing research, or we'll be doing homework or something, you know. We'll come across some really complicated looking calculations. And what do we think first? Well, we're intimidated, of course, because, I mean, like, we're at high school level, and we haven't even come close. Like, that's what we feel anyways. We haven't come close to learning these things. So, what does PBL offer? What does STEM offer to us? A simple demonstration that can lead us to these things. These simple demonstrations allow us to understand the concept first, and then know that the calculations will come later. It's just knowledge that you'll attain after you've seen it enough, you know? So, I will expand on the second page, so if you can turn the page over, please. Here is a much simpler example, well, not example, but an explanation. It offers insight into what centripetal force is without intimidating you. And there's visuals on this page as well that allow students to relate centripetal force to something they see in their everyday life. For example, the car, when you're going around a turn. The concept that's occurring here is centripetal force. But the people in the car are forced outward. Now what is this? Inertia, right? Your body's in motion, so you have a tendency to remain in motion, in a straight line. So when your car turns to the left, you have a tendency to be in motion. Now these are all concepts of centripetal force that can be related to real life. Here's an example of one demonstration. This is my little brother's soccer ball. I borrowed it, and a piece of twine here, okay? And as I rotate this, you're seeing the same concept that is holding the car in the turn and the roller coaster, right? So centripetal force here is the string. It's a tension acting on the ball. So centripetal force is a center-seeking force. So it's a force that's pulling this ball towards the center, a pivot, which is between my fingers here. So when I rotate this, centripetal force is pulling the ball inwards, keeping inertia from acting on it. So if inertia were acting on it, the ball would go in a straight line, right? Perpendicular to the centripetal force towards the center. So if I release the ball up here at the top, it'll go 90 degrees, so it'll go that way, okay? And this is something that most kids don't understand. Like, if I release it here, well, which way is it going to go? Most of them would say that way, you know? It's going to continue going in a circle. That's not true. So, like, there are many misconceptions in science, and this is one of them. Now, my second demonstration here, well, I had to modify a little bit because I thought the flue would just be boring, so I attached some flashlights to it to make it a little more interesting. Would you mind turning Thank you. So, as I turn this on, you will note that two things will be happening here. I'll pause and watch you and let y'all see the effect, and I'll explain it. As this is gaining speed, you will see a parabola. But why, right? We started out with just water. Like, how does this happen, you know? This is something that, honestly, it attracted me to this concept. Because I've never seen the demonstration before, though you see it in everyday life. Like if you've been in a swimming pool, you're swimming around in a circle. Or if you've seen a bowl of water that's spinning. Some of us have like turntables at home, like pottery sets or something. They have a turntable usually. And they were interested as a kid, so you wanted to see what would happen if you put water in there or something. So sometimes we've seen these concepts, but we just never understood them. Like we thought that they were just happening, you know. So here we have a combination of two things: inertia and centripetal force. But what most people don't understand is centripetal force centripetal force varies depending on the demonstration. Like earlier, it was the twine, right? It was exerting tension on the ball, keeping it in a circle. And this one, it's gravity, right? Gravity's holding all the water down. And another thing most people don't know is that gravity, because of Newton's third law of motion, which states that for every action there's an equal and opposite reaction, there is a normal force. Okay? So gravity is pulling something down, but it's also exerting a force upward. When I drop this, it bounces up, because the ball is exerting a force downward, and the floor is like pushing it back up, basically. It's having a force in the opposite direction. So it's the same concept here. So we have normal force, which is pushing the water upward, right? So that's adding to the parabolic shape, but it's the x component, because centripetal force, normal force can be split into two components. That's where it gets a little more complicated. So your x component of your normal force is pulling this water into around a center. Okay? So the combination of the inertia, which is being created by the rotation, the water is wanting to go out. Okay? And since it's in a container, it starts going up. This combined with the centripetal force creates a parabolic shape. Now these are concepts they're a bit difficult to understand if you don't go in depth, but it offers some insight into something that looks really interesting. Now I'll pass it off to my friend George.
Thank you, Johnny. Hello again. Now, you've all seen centripetal force explained, and you've seen centrifugal force dispelled as a myth. But what I want to talk about is resonance. And what resonance is the tendency of a system to oscillate. Now, what this means is if something has a frequency, let's say, I don't know, the Tacoma Bridge, like in 1940. Does anyone know about what happened?
The suspension bridge.
Yes. That has a natural frequency. Now, the shear winds that pass by every summer, especially those, they're part of the jet current, the one that runs through the U.S. from west to east. Anyway, the shear winds had the same natural frequency as the bridge, and because of that, they formed a system of resonance, and the energy created by that caused the bridge to just rip apart. By the same principle of resonance, we can create very cool illusions using lights and a string vibrator. Now, right now, you can see that it looks like it's just wiggling very slowly, right? Does everyone see that? Yes?
Mm-hmm.
Now, if I make the system resonant right here, it freezes. Why is it frozen in time? The reason behind this is this has the same frequency as this, meaning that for every oscillation, there's one flash of the strobe light. This allows the light to reflect off the string at the same point of every oscillation of the string. Now, if I turn this up a lot, like a lot, right there, you'll notice that there's many points where it curves. That's because the high frequency has higher energy transfer, and because of this, the nodes that it creates store the energy more. So the nodes are basically parts of a system of resonance that store energy that's transferred in the system of resonance, such as the bridge and the winds. Now, the antinodes, the path along which the energy travels, causes